Hello and welcome to this introduction to Apache Spark APIs for data processing. My name is Luca Canali. I'm with CERN IT, Data Analytics and Spark Service. I'd like to start with a very brief introduction to open source big data. In 2004, MapReduce was introduced and Google revealed how they would do data processing at scale at the time. In 2006, Apache Hadoop was born as an open source implementation of MapReduce, and also later grown with the HDFS and Hadoop Yarn. Some performance problems were apparent when using MapReduce scale, and different projects, including Apache Spark, came out to fix these problems. In particular, in 2009, a seminal paper by a team at UC Berkeley came out introducing Spark, which allowed to have more usage of memory and introduced this resilient distributed dataset abstraction that is the key on the underlying engine of Spark. Then Spark has continued to grow, and in particular in 2015, Spark SQL and DataFrame APIs became the main APIs for using Spark. And since then, Spark adoption has grown and now is used considerably in industry, from Databricks, for example, who is a company founded by the original authors of Spark. And then other large companies use it, like Apple, Netflix, and they also contribute to its development. As I record this, the latest release of Spark is 3.3.0. So what is Apache Spark? It's a unified analytics engine for large-scale data processing with an expressive development API. This enables the processing of large data sets and allows for sophisticated analytics, real-time streaming, and machine learning. Let's put this in context of a large ecosystem. So we have a core engine of Spark. This will be the engine that is implemented using Scala and Java, runs in the JVM, and uses the RDD abstraction. On top of it, there are powerful APIs. We particularly see in this course Spark SQL and DataFrames. We will also have a brief introduction to Spark streaming and machine learning. There is also graph processing. Multiple languages are available to work with Spark: Scala, Java, Python, which will be a focus of this course, and SQL also, which we'll see in this course. And there is also R, which is less used. In terms of use cases, as we have seen in the previous slide, we have data analytics, streaming, machine learning, graph processing. So where can we run Spark? We can run it locally. For example, when we develop on a laptop or a small resource, we will use this type of way of running Spark for many of our exercises. And then Spark can run at scale. That's where the magic comes out. It can run on Hadoop Yarn, but it can also run on cloud systems using Kubernetes. And there is also a standalone cluster that comes with these Spark binaries that allows to build Spark clusters on top of any resources. And then there are many other integrations. For example, Spark can ingest, reading and writing many common open data formats: CSVs, JSON, Parquet, Avro, and is also extensible. For example, there is an extension to read root files of interest for physics. Spark can interface with many storage systems, Hadoop, and then there are extensions, for example, for the CERN EOS. Spark can read and write to and from relational databases, and then can work on streaming data, on cloud data, for example, on S3 and other object stores. So how does Spark work? So computation are distributed across several nodes in a cluster when we are using a cluster, and then they optimize it for running at scale, and then fault tolerance is also an important part of how Spark works. This diagram shows the main components when using Spark. So we will have a driver, let's say our laptop or desktop machine, where we are running the computation. Here we will have our user code, and we will allocate a Spark session. We'll have more on that, which is the main abstraction that allows to talk with the cluster manager and the executors. So the cluster manager will be used to ask to spawn executors to scale out the work, and the executors will be many different JVMs, and also Python workers that allow to scale out the work. So Spark session has a one-to-one correspondence between the Spark session and the Spark application. Spark session is the entry point for all user-defined data processing, and in practice, as we will see in the exercises, we will have a variable Spark when we start using, for example, from the Spark console, the Python console, or the Jupyter notebooks. Then the driver is another key element. That's where the Spark session is created, and the Spark session resides in the driver. This distributes and schedules work across the executors. It manages the executor's lifecycle, and that's when we're using the command line. That's where we'll have the Spark driver, or in our Jupyter notebooks when we run the Jupyter notebooks examples. Spark executors are responsible for carrying out the work assigned by the driver, and they can run it at scale. They can read and write to and from storage, HDFS or cloud storage or other resources, and then they can also be used for caching data in memory, and in general to perform all data processing operations. Two main class managers of interest here are Yarn, a class manager for Hadoop, and then Kubernetes for cloud resources. And as I mentioned earlier on, there is also a standalone cluster that we can use to manually set up a cluster, for example, on a group of VMs. When we are running on Spark, we can run in client mode. So the driver is external from the cluster in this case. It could be your desktop or dedicated host. And then we connect to the cluster. Or for batch mode, we can have also the driver running in a cluster. That's the way we submit jobs, for example, to Yarn or to Kubernetes. Spark data frames are a key abstraction in Spark. Spark data frames are the higher level data structure that are implemented using an immutable distributed table of records with rows, columns, and a schema. Schema is very important as data frames are for processing structured data. Data frames are analogous to databases, for example, tables in databases, but here we don't have indexes or primary keys. Or if you're familiar with other environments in Python, for example, you may have already seen pandas data frames, also R as data frames. It's important to note that data frames are divided in partitions and are distributed across multiple executors. This diagram that comes from the reference here, it shows the structure of a data frame, and data frame is similar to a table. It's an abstraction similar to pandas or databases tables. And those data with a schema, as you can see here, we have a schema. And data frames are partitioned. So there are collections of rows grouped into partitions, and these partitions are immutable, which enables parallel execution and also fault tolerance. We will see that if a partition fails, if a job has a partial failure, then only work on a certain partition can be redone, as opposed to restarting the entire job. Actions and transformations. There are two types of operations in data frames. Transformations will transform a data frame into another one, and examples are filter, select, and order by. Transformations are operated with lazy evaluation. And transformation will not trigger computation. Computation is triggered by actions. So when we finally ask Spark, for example, show me the results, or count the number of elements in a data frame, collect, or write the output to, for example, to HDFS. At that point, the operation is performed. There are two types of transformation that you should know about. There are narrow transformations that are more performant because they will be executed just in one pass in memory, and wide transformation that result in data exchange between many nodes in a process that is called shuffle. Shuffle is very important for distributed data processing, and its optimization is key for high-performance engines like Spark. This diagram shows what a narrow transformation is. On the left, that's when there is a dependency, a simple dependency between the input and the output. Like it could be in a filter operation, a select operation, or union. Operations like group by or sorts, however, will have a wide transformation. So input partitions and output partitions are have all sorts of complex dependencies. And in the middle, there is a shuffle operation, which can be quite expensive. Think, for example, of sorting terabytes of data divided in thousands of partitions. So actions instruct Spark to compute a result from a series of transformations. And there are actions for viewing data in the console. That could be like show, or for collecting data into native objects. For example, we can collect into pandas data frames, or we can write to external systems, HDFS, S3, EOS, etc. Lazy evaluation is very important. So transformations are lazily evaluated. Only at the end, when we trigger an action, Spark will evaluate all the chain of transformations that go from the input data to the output data. And also the data frames are immutable, which allows for scaling out and fault tolerance. So transformations can be replayed only on parts of the data, partitions in particular. Let's see an example. Here we define two data frames, and then we want to filter the first data frame and join the two data frames and then apply a count. Filter and join are transformations, and the count is an action. We'll have more examples, of course, in the demos and tutorials. So what about execution? Invoking an action creates a job, which is then divided internally into stages and tasks. Spark will trigger the creation of a graph of computation called DAG, and will divide it in stages and tasks. Tasks are the unit of parallelization, and they run concurrently in the executors. Typically, a task will operate on one partition of the data and will run on one executor and on one core of that executor. Stages are collections of operations that together will form jobs. We can see how this works from the web UI when we run some Spark jobs. This is a snapshot of the web UI for this type of operations, where we can see that the data is read, then is filtered and joined, and finally a count operation with the required shuffle is done. The web UI will also show us all the jobs that are there, the details of the executors, and details of the data frame operations that happen with some performance data inside it. We'll get back to that when we do the demos. So a few important points about the DataFrame API. Schema is key because we are processing structured data. So we have column with names, data types. And schemas can be inferred in some cases when reading data, if we are thinking from reading from a source, let's say a CSV, but it's better to define and specify it. And very importantly, there are data formats that store the schema together with the data. Let's see how this works in practice. Let's say we have this table with a list of scientists, and then we define the schema with ID, which is an integer, and the name, that's a string, and surname, also a string. And then we read from CSV. Let's suppose this data is on a CSV file or a collection of files. And then we put the file names and the schema. Otherwise, if we don't do that, for example, Spark might try to guess that ID is also a string, or something else can go wrong if we specify the schema is more precise. And if we are using data formats, we'll get back to that in a future lecture. Like Apache Spark APIs, schema will be inside the files. So we travel together with the data. So columns are also quite important and are similar to columns in databases or pandas data frames. We can address columns with this type of syntax. Then we can manipulate them. For example, we can create a column from a computed expression. This could be the expression and the name of the column. This one, for example, is even, and this is the expression A modulus 2. We can also drop a column. It's important to remember that these operations do not modify a data frame in place, but they return a new data frames. Data frames are immutable for the reasons of improving scalability and fault tolerance. Let's see some basic data frame operations. For example, we may want to do a projection First line defines a data frame. We will use that in the tutorial. And then we can define a data frame that is just a selection of the column ID, which contains the numbers, as we will see. And then we can have a selection. Let's say we apply a filter. We only have ID greater than 5. And something more complex that performs an aggregation. Let's say we want to sum all the IDs. Caching is also quite important, so Spark has the possibility to cache data in memory for faster execution. In particular, if we need to read a table multiple times, it may be convenient to cache it if we have enough memory to do so. And it's important to note that cache is lazily evaluated, which means it's only done when the first action is run. Often people run a count after caching to force the caching of data. And it's also possible to unpersist the data to remove it from cache. We will also see this in the demos. Which brings us to the end of this lecture, and I would like to mention some key learning points. The first one is that Apache Spark is a library and a framework for data processing at scale. It has a large adoption in industry, and it has many integrations with storage and computer systems. And then the Spark DataFrame is a key abstraction. It's scalable and fault-tolerant abstraction for processing data with a schema. It has a rich and powerful API for processing large data sets. And we will see more of this in the tutorials and demos.